right. So in session 2, we will be talking about the analysis chapter. And just for a quick overview, I copy and pasted the main objective that the author put in the book. So the idea is to talk about the what and why of algorithm analysis. And for this, we sort of need to talk about what an algorithm is. And then we get straight to big O notation and talk a bit about the big O execution time of common operations. Especially we'll talk about lists and dictionaries. And I think in the book, someone mentioned he or she, I didn't even check the author, that we would go into like the average time and the maximum time or minimum time, but I don't think we are getting there yet. So maybe that's the next chapter. And then we'll talk about some differences in execution time of lists and dictionaries. And he used some examples with the timer module, which we could also look into. So yeah, did everybody get around to reading the chapter before you go ahead, or did anybody have any special struggles with parts of the chapter, so we can maybe focus on those if you like got stuck somewhere?
So I don't know if you'll get to it, but for me, the one thing that was confusing was how to understand if an algorithm is like log time. Like it's very easy and obvious to me to say, look at something and be like, okay, yeah, that's linear time. That's like, n squared, that's n cubed. But I wasn't really sure, like a couple of times I guessed with the like, check yourself, like, oh, this is log time.
Makes sense.
But I wasn't really sure like what the intuition was.
I think there's only one small sentence in the part, but it makes sense once you find this one sentence. So I think we get to this when we talk about this. I can point you to the sentence, I think. And then I think one important thing we should focus here is that we are talking about algorithms. It doesn't really matter what program or what language we're using to implement those. We just happen to be using Python. An algorithm is just a series of steps to solve a problem. It doesn't matter if you're doing this as a human with a piece of paper or with some programming language. So this is independent in a way of runtime, for example. You could use a language that is closer to machine language, for example. All right, big O. When we talk about big O, there's always this N, and N is the size of the problem, which is a very general thing to say, but for most things, it's fairly obvious. For example, when you're talking about a list, it's the length of the list that you're iterating over, just the number of things you have. For other things, it might be more complex, but well, we'll deal with those when they arise. And then say we have an algorithm that does a number of steps to solve a problem. The number of steps is then this function t. T of n is the number of steps. Or, well, they say time here, but it's not really time. It's more like the number of steps, because the time is actually dependent then on how fast you do each step, which doesn't really matter for big O notation. And then what we want to get to is this order of magnitude function, which is the part of the function. Well, they interchangeably use t and f. Let's say f is the program or the function that solves the problem that t describes. Then the order of magnitude function, the big O of this problem, is the thing that increases the fastest. So if you have really, really large n's, some smaller values just become less and less important. So we only focus on the very, very big things. Say we have a couple of functions like those. Down here, oh, I made a looping. That's not very clever. But in green, for example, I just have a constant value of 1000 where I add x to it. And as x increases, it increases very, very gradually. But then if we have, for example, 100 times x, it increases a lot faster. But then even more, for example, it's just 10 times, but x squared. So as x squared increases, as x increases, it just grows even faster. And then if we take it even further, we can say maybe x cubed, for example, or I don't have this in here, but we could have, for example, 2 to the power of x, which would then be this one, the exponential one, which is, yeah, the static image that you saw in the book. And the tricky ones are log linear and logarithmic. So let's talk about those, I think, now. So I think there's one good intuition. If you are, say, you're iterating through a list, you usually end up with linear time. If you are iterating through a nested list, you usually end up with quadratic time. So it's basically you are looping through each combination of things, which gives you the square of the things. But if you have a problem where every time you do a step, you cut the problem in half, like a divide and conquer algorithm, then you end up with something logarithmic. Yeah. And the reason for this is if we think back to like high school math, which has been a while for most of us, I assume, you might remember the calculation rules for logarithms. And there's one striking thing there, because logarithms are actually able to turn multiplications into additions. Mm-hmm. So anything that used to be a multiplicative effect will now be an additive effect. So yeah, now I'm a bit unsure how to finish that train of thought. But that's what came to my mind when I thought, oh, it's something that we are halving the problem every time. It must be logarithmic. And the intuition is behind this is because logarithms take multiplications into additions or subtractions, depending on.
I'm going to have to spend time Googling this. I'm still like, that was also my rule of thumb. I was like, okay, if it's going to like reduce the number of steps the further we go, then it's log linear. But I'm still not totally sure why it makes sense for it.
Yeah. I agree.
And then staying with log, but I'll do some Googling after this, see if I find anything that convinces me.
And then getting into lists and dictionaries, where we're talking about the common operations on lists. What I find interesting here is, well, the most striking thing is taking a thing off the end is just O of 1, so it doesn't really matter it doesn't even matter how long the list is. Putting something to the end, it also doesn't matter how long the list is. Just if we want to get a special element from the beginning or the middle of the list, it depends on the length of the list.
So I was reading, I guess, because he talks about like how I can't remember if it's in this chapter or something else I was reading, why this is like the structure they use is there's an acronym for it. First on, last out. Is that it? That's how the Python.
Yeah.
Yeah. First in, first out. Last in, first out. FIFO.
Well, FIFO would be first in, first
out.
First in, first out.
LIFO, last in, first out.
It's last in, first out. Right, you're right.
Last in, first out, which is why the pop
taking
is 01.
Is just the last thing off again. Right. And if you take the first thing off, you need to shift everything one step.
Yeah, you need to reindex everything. So that's why you need to go through all of it. And that was also why concatenating, as I understood it, was that when you concatenate, it doesn't matter how long your to the left list is, because you'll add it to the end, but you'll kind of have to then reindex from that point. So you'll still have like O(n)
basically
of
your second
M
list that you're adding
or something. Yeah,
which is why every time he's talking about the second thing, it's K, And the first thing is n. Oh, sort, interestingly, is n log n. So this is some divide and conquer style algorithm, I think.
There is a log n here, right?
Nothing log n other than like sort, which is n log n, which, yeah. There's a log there, as you say.
Oh, there's
divide and conquer.
no pure log n, right?
Pure log n.
Does it even exist?
Yeah.
I'm sure if it.
Yeah, it does exist, I think.
Is there always an n before that, or
log n?
Yeah.
Yeah. Just like divide and conquer approach, when you have a problem and you divide it into two, you keep dividing into two, so the problem reduces to smaller half. That is when you have log n. Runtime.
So sort or sorted, at least sorted, I'm not sure of sort, but it sounds reasonable, uses tim sort, which is a hybrid sorting algorithm, which uses parts of merge sort and insertion sort, but it's kind of clever. So the best case scenario is O of n, and the worst case is O n log n.
Yeah, so I think the sorting,
worst case.
The sorting use some kind of, if you remember the sorting algorithm, sometimes they use some kind of divide and conquer. So you divide the stuff into two, you sort them in some kind of order. So you, if you know the sorting algorithm, how they work, so when you divide a section, you try to sort them according to the order. And if the thing doesn't exist in this place, you discard the other half, you take another half, you divide it into some. So I think, so if you divide it into n times, so because basically the divide and conquer is log n, so therefore you have n log n execution time for sorting.
Does everyone, are we going to get into sorting? Has everyone peeked ahead? We must, right? Those are the later chapters.
I haven't peeked.
No, it was a task, right? Or a programming exercise on sorting. Or I guess it wasn't sorting technically, but you could solve it.
Sorting and searching.
Okay.
Sorting.
Yeah. Okay.
Yeah.
Because I'm like tim sort, merge sort.
Yeah, merge
sort. Things.
So if you remember merge sort, that is what they basically do. Merge sort, they do that kind of divide and conquer approach to sort.
Specifically, sorted uses tim sort, which is it's a hybrid between merge sort and insertion sort, but it will always, the worst case scenario is O of n log n, but the best case scenario is O of n, which makes it more efficient generally. And it's also fast when you have a relatively small n or a small list.
I'd say we get into those when we get to the sorting chapter, which is chapter 6.
Yeah.
And by that time, we will also be more equipped to have the proper vocabulary, I assume.
Yeah.
So just to make sure we're on the same page.
Yeah.
But one thing I think is quite nice that they included this discussion questions part. So let's talk about some of those. Maybe does anybody want to already give an introduction for the first one?
So this one I think is going to be n squared, right? O(n) squared, because we're going twice through it.
Yeah. Yeah, sure. The second one.
Interestingly, if you just run it, it's gonna be n squared. But it's kind of a useless program. Right? Just the same thing every iteration. So you could write this as O of 1. But it wasn't. So yeah, as it is, it's n squared, but it's not doing anything useful.
So my intuition is, so basically when you have 2 4 nested log, the nesting of the 4 defines how many n you have, right? So if we have 3 4, we have n cubed, right?
Yeah, that's my feeling too. So then basically that's like question 4 there. Is that 4 4 4? Probably cubic?
Yeah, this should be cubed.
Yeah, and that's true, yeah.
It's like you can think of a chessboard, and you're going through both things. so you end up with a square. It's just by the same sides. And then you doing this for a third dimension, so you end up with a cube. And then if you can think in 4 dimensions, well, I can't, but you end up with a hypercube in 4 dimensions.
So this one, I'm guessing is like the case of the log, right? Because we're having it with that. So for question 3,
yeah.
Sorry, I skipped. So I equals n while I is greater than 0, and then we have it.
Yeah, this should be, is it now log or n log n?
Should be log, right?
Log n, I guess. It's log n, I guess. Yeah, I guess, yeah.
Yeah, log n.
I also got slightly confused at this one to some degree because I was thinking, like, I'm sure I've read somewhere that if you keep dividing something by 2, it will not eventually equal 0, right? There's some like mathematical like puzzle about that, right? Like if you just keep going in half, you're not eventually going to equal 0. But I guess
but so you use integer division, right? Or floor division.
Oh yeah.
Then you will get 0. Else you'll have an inf loop.
Yeah.
That's what oh my gosh, I was like, that's gonna run to infinity. No. Yes, I see that.
Right. And the last one is also interesting because we do have 3 loops, but they're not nested.
So what is the order of this?
So it should just be
O of n? Yeah.
What? Yeah, on.
Okay,
it'll
on.
Just be, 3 on.
Yeah.
It will take longer. Of course, it will take longer than just one loop. But the order of magnitude is still the same.
Yeah. So here it will be order of O 3n, right? 3n.
You abstract the numbers in front of the n, since it's just multiplied by. It's only when you have like exponential things it matters, or like when you have something depending on the k or whatever. So you can it can be like 100 or whatever, but you still.
Because it's too small. It's insignificant, the constants, right?
Yeah, if we imagine n going towards infinity, it kind of diminishes.
Yeah, gotcha.
I mean, it's still going to be longer than just 1 or 2 loops, but the order of magnitude doesn't care about those.
So I don't know if he said this in this chapter, but is this the chapter where he said you should consider the amount of time you optimize as a part of the time of your algorithm, or have I read that somewhere else? Maybe I read that in another book.
It might be somewhere else, but it's a good point. Yeah, definitely a good point.
Is like, you should consider, it was another book I read actually. You should consider how much time you spend optimizing an algorithm as also a part of that algorithm's runtime. If you spend 2 weeks optimizing an algorithm and gain 5 seconds.
Yeah,
there's also this XKCD comic about it, and there's this this quote by someone, I don't remember who said premature optimization is the least of all evil.
Yeah.
It has context though in that quote, but it's pretty much it.
Yeah. So I think he is the author of algorithm book who introduces analysis of algorithm.
Okay.
Knut, what is his name? Knut.
Knut,
yeah. Knut.
Donald Knut?
Donald Knut, yeah. Right. Donald Knut. He made that statement that premature optimization is the evil of. So the point he making that is like when you're trying to write a program, get it to work first. Yeah. No matter how worse the program is, get it working, and later on you come back and optimize it.
Yeah, it's a paradigm, right? You have make it work, make it right, make it fast, and often you only have time to actually make it work.
Yeah.
And I don't know, people disagree about the order of making it right and making it work. For example, if I'm manufacturing a medical application, I would prefer programmers who don't make a program that runs but doesn't run right, over programmers who just make everything run without caring if it's right.
But we'll have to think about the like what would be the definition of right. I mean, right is to completely adhere to the style guide of the language and
that's a
kind of
question.
optimize. Making it work is that the tests pass. It does what it does, and
but
it
you
works.
can write programs that work from the perspective of the program and the programmer, but they don't provide a correct solution to a problem.
But they don't technically work. I think the point is that all your tests should pass. It doesn't matter. Like the implementation is not important yet. Just make it work and the test pass. Then you can go into like doing all the fancy stuff and like making it pretty basically, like, and maybe optimize or just like making it more readable.
That's a different question. That's completely out of the question when you talk about make it right.
I must have misunderstood that quote then, because making it work, I assume, is to actually make it behave as you expect it to behave. And making it right is to actually like
they sort of go hand in hand.
Yeah. I don't know.
All right, maybe we can move on to the exercises. Did anybody do the complete exercises?
I did the first two, and then I got totally like lost on the third one because it's not complicated, but for some reason my brain just got broken about how to use the timer module.
The timer module, yeah.
Yeah. So I'm happy to share my answers for the first two. If
sure.
anybody wants to look at them.
Shall I stop sharing and then?
I think I've set it up so that anybody can steal sharing whenever they want.
Oh, okay.
I think this works properly.
Go ahead and
try. It work?
Oh yeah, I lost sharing.
Yeah, okay.
Yeah.
Okay. So the only reason I want to show this up is that I gave up plot 9 a try for the first time today, which is the only reason I thought it would be cool to share today.
It's like a ggplot thing for Python.
Yeah, it's ggplot for Python. So I think it's fairly easy. So devise an experiment to verify that the list index operator is a 1. So you set up your timer object. Here, what I decided to have it do was, rather than just pulling like indexing from I, because I was like, maybe that's not totally fair considering that, I don't know why, I just wanted it to index from something slightly different than I. So I just basically said, okay, the thing the timer is going to run is X, index I minus 4, and then import XI. And then I made a list, which is like this. And then I run it from 100 to, that's not a number, 100,000 by steps of 100, make out my list, and then use my timer object here, run it 1,000 times and append it. As we've learned, we should append and not concatenate to grow a list. Quickly make a data frame, which is essentially just going to be the sizes of the list and then the times. And then I use this plot 9, which is basically, if you don't write in ggplot or in R, you won't have, I don't assume it's going to be like super obvious and intuitive to you. But since I do write R and use ggplot a lot, I was like, okay, I'll just use this because I really hate Seaborn. Sorry, I don't like it at all. But yeah, this is my thing. Use plot 9. It was super easy to use. So you can use it exactly as a ggplot object. You put it in between these brackets, and then you call it plot 9 ggplot data, plot 9 aesthetic, and then kind of exactly how you would do a ggplot object. And yeah, we can verify that basically that as the list size grows, there's some kind of minor fluctuations, but it's pretty steady. So that was my verification. I don't know if anybody else did anything else different. Did you do it differently? I'm super happy to see the solution.
No, I think I would have done it the same thing, except I just completely gave up on plotting in Python and plotted with R. So yeah.
I mean, I also gave up with plotting with Python. Plot 9 is just an R port. And then basically for the next one, devising a experiment to verify that get and set items are O1 for dictionaries. I essentially did the exact same thing. So a timer, and here I have a dictionary. And again, I'm either going to get from the dictionary, so just querying it, or set it. I create 2 different lists, which are going to be storing my times objects later. And then I loop through in the same way. The only difference is the way I grow the dictionary here is that I basically make 2 lists. And then for the dictionary, I zip it together, create a dictionary, and apply it here. And again, I at least find the way the timer module works a little bit funky. So this, like, the how you do it of like, okay, the first argument here to this object, I guess this is the initialization of the object, is the function, and then we have to call from what environment we're importing things. So I find this a little bit funky here. And then just kind of the same thing. So we can plot it here. And again, stable for getting times, stable for setting times. So, and then I started doing this part, and then I was like, oh, this isn't going to work in the same way. Now I'm going to have to make a function. And that's where I stopped. So that's what I got.
All right, it's about the del operator.
The del. So basically I tried to do the same thing, and then it obviously immediately didn't work because you say when you do the timer thing, do it 1,000 times, and it didn't have the same thing 1,000 times. So it wasn't going to work. So I needed to make a new function that would generate every time, and then, yeah. So I'd love to see your answer, basically.
Shouldn't this just be a variation of what the book did for showing how pop and pop 0 work? Because pop and pop 0 also modify the list, just like del does. So if I show this part, this is basically, so I took the code from the book where he printed something for pop and pop 0, and then he made a graph underneath, but he didn't show how he made the graph. So I did something that, just like you did, I made a list for the n's and for the t's, for example, for the time for pop 0 and the time for pop, for example, just empty lists. And then we grow the lists in a loop. We loop over all the different n's. First, we create a list of this size, and then we use this timed thing. And the interesting thing about this here is we are creating the timer up here, and what it does is it imports the variable x from just the main script. So whenever x is updated at each iteration in the list, we get this new x when we're doing the timed. And then I only ran it 100 times instead of like 1,000 or 10,000 like he did. And I think we could do the same for del. I haven't used del yet, so let's try this. So we have del here, and how does del work?
So I think you give it the index, right? I had to Google it as well because I had never used it either. So I think it's something like, but this gave me an error, so maybe this is not right.
Are you getting the item, like indexing list, and then just run del on that? Or like as a statement, del space my list square brackets index?
So if I type del space this, no, okay.
You need to index it, right? Did you have square brackets? No.
Oh, it's like this.
Yeah, it's like this item from this list we want to remove.
Oh, right. This is Python. Now I should have deleted the first one. I forgot what the first one was. Yes. Okay, it's working. Okay, del ns. So this would be x. And then it shouldn't matter which del, I guess. So we can make it random. But that would be just too much work. Let's use the first one. So something happened. I used T0. Maybe I should have called it just T. We got some times. And now because I'm lazy, the ends, let's call this T. Oh, yeah.
That looks fairly constant.
That looks fairly constant, yeah. That looks suspiciously constant.
Yeah.
Did something break?
Maybe that's just how long it takes. I don't know. But
I mean, in your plot, we had at least some fluctuation, which
a little bit of
makes
jitter
sense to me. If I decrease the number, we should see more fluctuation if we have fluctuation. No? Let's just do it one time for each thing. Well, okay, it looks constant, but I'm a bit it's a bit suspicious here.
The times are the same, right?
That is really, really close, yeah.
Aren't they exactly the same? If you do a set, convert that to a set and see how long it becomes, how big it becomes.
Oh, that's a cool thing to do, yeah.
Yeah, they're all the same.
All right, so apparently there's no fluctuation in del x0.
That does sound suspicious. Did you empty the list? Is it like an index error or something? No.
So I got a key error when I tried to do this.
A key error?
Yeah, that's what made me think that I was doing.
You're using dictionaries?
Yeah. So this one's supposed to be comparing lists versus dictionaries. I just flopped the code that I did to test it in, but it's very possible I'm not doing it quite the right way. This is what made me think that I'm not generating the list properly.
All right, now
correctly.
I have an empty set. Something's weird.
Yeah.
Let's see.
It does work when I remove the first element.
How long is it? Like, do you have like some?
What if you try like
reading code like this?
The 10th element.
It's 100.
Oh.
So, I have a suspicion.
Index error?
Yeah, now I should get an index error. Yeah.
So
I think I was wrong about the time it thing. Maybe if we run it 10 times, it uses the same X.
But you're using F strings, right?
Well, he's using F strings, yeah, but I'm not.
Was it?
Yeah,
you are. Or I mean, there you were.
Yeah.
So
Not
you're
really.
basically hard coding, since you have the like you have quotes inside inside the color braces, which means that you're using, instead of doing like numbers, you're using strings. Wouldn't that be it? If you go back, because you have F on 168.
Oh, this is just the first that.
Oh, that's just a print. Never mind.
It was just a printing for the table that you had.
Oh yeah.
We're not using the table anymore because we are plotting something.
So remove that from that.
So we should get a new X every time.
But the end. Okay. Never mind. I just said.
Oh no. I'm printing too much.
Yeah.
I've never used a time. I maybe use time it like once. I usually like write a decorator. That's probably not as pure, but I find it's more intuitive to kind of just decorate your functions that you want to test.
Does make sense, yeah.
Like when you want to compare, and then you can have the printout like one. And you don't necessarily need to, depending on if you want to use the time or not. If you just want to see it, you can just print it inside the decorator. And then you won't have to like adapt your, I guess you can still, since you're using a decorator, you can still adapt your return statement without actually touching your function. So I love decorators so much. But yeah, I thought the whole time, like the whole time it module, like the API, or it was slightly, I don't know.
Yeah,
it's a bit confusing. Yeah.
Yes, exactly. That one. Not super intuitive.
I broke it. Does somebody else want to share?
I mean, I can show you the non-working code on my screen, and maybe this will like make things more clear. I don't know. So yeah, this is how I had tried to solve it. I think it's essentially the same concept. So you make the timer, a dictionary, a list, and then this was just to check something. So we generate our keys, our list, our dictionary, and then this here number 1,000 means like repeated 1,000 times, right? So I'm not sure if something is going funky here.
I think so. What happens if you reduce it down to 10?
Okay, 10.
This would indicate that it is indeed using the same list and dictionary for all the iterations, which would be kind of stupid.
Yeah, so I get this key error, which makes me think then that what's happening is that, for example, now we say a dictionary.
Oh, wait a second.
You're removing 3. You're removing 3 from the dictionary multiple times, right? Like how many times do you run?
So it's supposed to be running here. I mean, ideally what it does is
that's probably why you want random. That's why you want random, why you want to pick the I from random range, because then you won't run into
random won't help because we can still run into it.
Or random, no. If you pick the index to remove from a range, you have distinct numbers in that range. You won't run into a key error, since you won't try to remove the same key multiple times.
But my thought is that what it was supposed to be doing is every time, and that could be that I misunderstood it, is that every time it's supposed to re-import this dictionary back from this environment, right?
But
so we create the dictionary here, which as I thought shouldn't have been touched by what happens inside of this environment here. Does that make sense? So from my reading of the time it thing, you should be importing you should be creating a new environment which has the dictionary object, and ideally that makes it clean of everything else. And so it should every time it runs it, it should re-import the dictionary, and it shouldn't A, give me this key error, and B, it shouldn't have touched the thing that was inside of this after running it. So I think that's just a misunderstanding of how time it works.
Would that be an issue? Would that be an issue with dictionaries being mutable? Since you're efficiently importing the same modified object multiple times.
I wonder if that could be something to do with
what if you do a copy?
Like
a deep copy?
Oh, before we delete
I think just a copy is probably fine.
Is it just like this? Copy?
Just a copy, since you have no object.
Shell copy.
We need to create the copy first and then delete.
I think you do. Yeah, I mean,
Can you do two statements inside of there?
Yeah.
Ooh.
Can you do multiple statements in Python in one line?
Let's try.
Can you do semicolon things?
Yeah. No. Yeah.
Copy
kind of.
Copy a dictionary?
Yeah.
Is that just copy? I
think you call copy on the, yeah, I think you call
the object.
It's a method on the object.
I can never remember. But, okay, and then we can try del copy 3.
Yeah.
See if this gives us an error. Let us see. List assignment out of range.
Oh, you're doing it 1,000 times, but the first I is going to be 100. Oh no, this shouldn't matter. Sorry.
This shouldn't matter.
It's the times, right?
Yeah, because this should just be the length of the list. So we should. I mean, our list will either be 100.
But now we do need to do the same for the list. The copying.
Heck, we're not even getting to that area yet. Oh yeah, we are.
It is removing the third element, but then it's doing it again and again 1,000 times. So.
Yep. So let's say copy, and then is it just a list copy?
Mm-hmm.
Hey.
Okay.
Hey, look at this. Something's happening. But then our lists aren't immutable.
Very mutable.
Yeah.
Yeah.
So
you would be using the same thing. I haven't looked at, I hate looking at code like this on the fly. I just want to delve into my den and read
now it's
things.
working, right?
I mean, it's running.
Oh, right, it's still running. Maybe you can reduce the number before we go ahead.
Yeah, let's shut down. Just stop.
Can you do a comma at the end of your dictionary? If you do a dictionary comma, then you don't get semicolon, then you don't get the output. If that is an issue, I can't see. If it's unnecessarily huge.
I don't think there's any output yet.
Yeah, there's no output yet.
Or okay, so that was the old one. Or
buddy, now I think I've killed it somehow. Start the kernel. Stop, Python. Stop running. Ooh.
Stop the count. No, Python doesn't want to stop the count.
No. Okay.
That's the reason why you should never use a bare exception. Then you can't stop it. If you have an exception and you accept it without specifying what kind of exception you run it in the REPL, you can't abort. Because it will catch your key interrupt error and say, okay, thanks, that was an exception. Moving on.
What are you so mad about? Kernel started. Okay. You seem to be functional. Sorry. Why is this taking so long? I'm just trying to import some libraries, man. Okay. Moving on. Okay. So we were on exercise 3. Yeah. We'll do this. Let's just do 10 times.
10, yeah. It's taking some time.
This feels suspicious to me, like we've done something wrong.
Well, you're also going up to 100,000.
So, yeah, maybe let's go up to.
And
I mean, it still shouldn't take this long. It was relatively fast when I was doing it on the shorter things. So I don't know. Let's go to 1,000 by steps of 10.
yeah.
Oh, okay. So.
Yeah, we got some times.
Times popped out, but that still seemed very slow. Is the
Do you still have
copy?
your plot code? Your plotting code
Yeah.
underneath?
Let's get that.
See what it.
I mean, technically the copy will. That's probably at least Irvin.
Yeah, that's gotta be at
depending.
least okay, right?
Okay, yeah, maybe. Or would it be our time scale? Since you have the thing and then you have to do it again or whatever. I'm checking out.
Let's see. Deldict times.
Right, the copy's going to be.
Yeah.
It
And
has to copy every element again, right?
yeah. So that'll be adding okay.
But how did this work with the previous examples? Because I mean,
because these ones weren't
it...
deleting anything. They were just getting
at
a setting. So
but
we were getting the
popping
same.
Was.
Yeah, that's the thing. The popping should have deleted it.
Yeah, the popping shouldn't have worked the way it did.
Yeah, that's why I'm like.
Oh no. It when I modified the code, it stopped working because I was just removing too many elements. So maybe it works if we remove just everything up to the last one.
Okay, is this right? Let's see.
But then again, it wouldn't make sense because we are not working on a list of lengths n anymore because the next iteration will be shorter.
Yeah.
Are
you gonna work? Okay. So that seems to be growing. But at what were we supposed to prove this was at what speed? This should be 01, right? If it's setting in a dictionary.
Yes, but we're also
deleting.
We're deleting. Yeah.
But we're also
doing the copying, and the copying.
We're also doing the copying.
N.
Okay. O-N, yeah. Which is growing.
Just N.
Yeah. Just N, yeah. Which is growing at the rate we expected to.
Kind of linear.
Yeah.
Which sort of proves it though, right? Since the thing we're doing is O-N, 1.
Yeah.
So we solved it, but it's probably not the right way to do it, but it works. So now we can go on and actually make it right. And eventually
the first
make it fast.
Okay, so then I guess the lesson is I need to go figure out how timer works and at some point convince myself that log makes sense for things cutting in half.
That's like a plan. What if you imagine like a phone book and you want to look up a name, then you like open it in the middle and then you know, okay, I'm looking for T, so it ought to be in this half. And then you just open 1/4 of the book, like the second half, you open that in the middle and then you can see which side should T be on. And then you go like that until you've kind of, that's like the basis of divide and conquer.
I mean, I get it. I like get it conceptually. To me, it's just like the log connection between the two doesn't make sense.
Yeah, that's just.
I believe there is someone who has explained it on YouTube. I believe in YouTube.
Yeah, probably.
Probably through Program Brown.
Yeah. I didn't do the next ones. I don't know if anybody did.
I did.
I didn't do them either.
Yes, accidentally. Or I've been using a PDF version of the book because I got myself an e-reader.
Do you want to share
money? No, not really. No, I kind of sort of accidentally solved one. I did the n log n because basically you just sort it and then you take k minus 1. Or is it K? K minus
Right,
1.
yeah, that makes sense.
K, probably. Okay, I can't think. K or K minus 1. It's always off by 1 in some direction. But yeah, basically just like, or the other, you reverse sort it probably. No? Yes?
Right?
No,
Yeah,
I can't think.
sorting
Anyway, you
is
sort
like-
it somehow.
You
And
sort
then
it and
you
then take some
index it.
Sort it and exit.
If
So
you,
given
yeah,
a
if
list
you just
of
sort
numbers
it,
in random order, write an algorithm that works in O n log n to find the K smallest number. So you sort it and then
yeah, then you take K.
that.
Right? Or is it K
Yeah.
minus 1? I can't
Yeah.
think at the moment. I seriously, it's
It
just
is
like,
either
that
K
one's-
or
that
N
one's
minus
K.
K,
Yeah. So
depending on how
it's find
sort
the
works.
is it N?
Does sort
If
put
it's
the highest or lowest?
descent, no, it's lowest.
Then it's just case element.
Yeah.
Yep.
I think like you start on 0, and I always get confused on like the whole off by 1 in any direction.
All right. Yeah,
But
it
yeah.
also depends on how the question was
Since-
meant. If the zeroth smallest number is the first number, but if the first smallest number is the zeroth number, but that's just a
Yeah,
different-
then it must be K minus 1, right?
yeah.
Because
that's
you're selecting the index, but it's like you start on 1 when you
Yep.
put it. Yeah, that's just always so confusing. Yeah,
And
so that
then
was the easy one.
could you make it linear?
Yes, kind of. It felt very, very hacky. But basically, I just ran through it K times and took the min, used the min function, deleted that one or removed it. And then I think I did a while K larger than 0. And then I just like targeted or found the smallest number, removed that from the thing, kept my index. It was I run min K times basically.
But if you're running K times, right?
Or a K minus 1 time. It was. I wouldn't say it was quite an improvement. There is a way to do this, and it's like very involved.
So if you want it to be linear,
works.
we basically can only go through the list once.
Yes.
So we loop through the list, and at each element, we write down the element. If it is smaller than the previous element, we
But it's not
write.
sorted.
Oh, that's just min.
Yeah, it's easy to find the smallest in one go. That's no problem. But basically, you want to do that K times. But since it's linear, it doesn't matter if we do it K, or technically that would be K. Kn.
Yeah. Oh, we can improve on that.
Yeah.
Just instead of only keeping track of the minimum at each point, we just grow a list.
Mm.
We just append a list with all the smallest numbers we have found so far.
Yeah.
And only if the number is smaller than all the numbers we already found.
But then you have to again go through that list. But I guess that could be fine depending.
You can keep track of a list of all the smallest numbers and the one already smallest number.
Okay.
And then we should in the end
tried something like that. So I did find a solution for the third largest number, but I assume I didn't want to go for the exact problem because I wanted to think. That was a nice idea. But basically, it was so ugly. They created 3 variables and then compared and did like different, but that feels just very cumbersome if you want to use K. So I did start on something using an empty list, or rather a list that had the start like nums 0 and then fill the rest with sys max or something like that. And then you would kind of go through that in some kind of clever way. But I just know I like sorted. It's a nice function. I'm happy that way.
So the answer
one
is
example.
go ahead.
Sorry.
No, I wasn't going to say anything helpful.
So I think the main thing to see here is that we have this trade-off between time and space.
Yes,
The
definitely.
first one is just very space efficient, but it's n log n. And the linear one is going to need more space because we need to keep track of more things.
Yeah.
We need to keep track of, for example, all the smallest numbers we have found so far. And in the end, we can end up with linear algorithm, but we have more memory we're needing.
Yeah, definitely. That's usually the trade-off. Though I forgot to ask, but O of n, as in not omega for sure, but O, that would be the worst case scenario, right?
O of n.
O of n is linear.
O of n. No. Sorry. O of whatever. Big O notation.
Yeah.
Because you have like the other. You have some Greek letters notation also, like theta.
Little O.
Yeah.
Theta.
Those were like you basically have notation for average case and best case.
So I don't quite understand your question yet.
So when you use big O notation, that would be the worst case scenario for a given algorithm.
Yeah, sure.
Right.
And then we have the best case and average case.
But we are not always interested about the best case scenario. We always want to optimize the worst case scenario, right? That is why we're interested in big O.
But when you use big O notation, that would be always refer to the worst case scenario. So if you want to use best case scenario, you have some other kind of notation.
Like other
analysis.
I mean, the best case rarely makes sense.
Yeah, it doesn't make sense.
But the average sense, like if you're talking about best case, random sort would be really good.